Hello everyone, welcome to the last minute revision tips for Physics Unit 3 exam tomorrow. So first look at how to take readings with Vernier caliper and micrometer screw gauge. So this scale is called the main scale, and the main scale reading is this reading of the Vernier scale before 0. So 0 in the Vernier scale, the reading before 0 is the main scale reading. So if you start counting from here, we have 10, 11, 12, 13, 14, 15, 16. So 16 is the main scale reading. And for the Vernier scale reading, you have to check which division aligns perfectly with the main scale. So you can clearly see. So this is first, second, third, and fourth. So it goes over here actually. So the fourth division aligns perfectly with the main scale. So the Vernier scale reading would be 4, and the equation would be for calculating a length with Vernier caliper, it's the main scale reading plus Vernier scale reading times 0.1, making sure all of these are consistent in millimeters. Why 0.1 everybody? Because 0.1 is the resolution of a Vernier caliper. So the main scale reading is 16 plus Vernier scale reading, again I repeat, the division which perfectly aligns with the main scale, which is 4 in this case, times 0.1, which is the resolution of a Vernier caliper. Now let's move on to a micrometer screw gauge. Always remember, every division of a micrometer screw gauge is 0.5 in the main scale, of course. This is the main scale. Every division is 0.5. So this is 0, this is 0.5, this is 1, and that makes it 1.5. And you can see some readings after 1.5. So the actual value is 1.5 something, right? So that something is what we are trying to find out. So for micrometer screw gauge, the same formula applies. Main scale reading plus rotating scale reading. This is the rotating scale. This part rotates, so that makes this the rotating scale reading times 0.01. And where does this 0.01 come? And why did we have 0.1 with Vernier caliper and 0.01 with micrometer screw gauge? That's because the resolution of a Vernier caliper is 0.1 millimeter and the resolution of a micrometer screw gauge is 0.01 millimeter. And the formula is main scale reading plus rotating scale reading times micrometer screw gauge constant, which is 0.01, or in other words, the resolution of the micrometer screw gauge. So the main scale reading was, this was 0.51 and this was 1.5. So 1.5 plus, we have to check which division aligns perfectly with the horizontal line of the main scale. So this is 20, 21 and 22. So the rotating scale reading would be 22 times 0.01. That's 1.72 millimeter. Next we have suitability of measuring instruments. In any measurement, the key objective is to always minimize percentage uncertainty. Now let's bring in the equation for percentage uncertainty. Percentage uncertainty is uncertainty divided by measured value times 100%. Now let's look at some of the resolutions and uncertainties of different instruments. When it comes to a meter rule, the resolution, the smallest division of a meter rule is 1 millimeter. In other words, the smallest value it can measure is 1 millimeter, and the uncertainty is always resolution divided by 2, and the range of values it can measure is 0 millimeter to 1000 millimeter. Vernier calipers have a resolution of 0.1, which we previously saw. The uncertainty is 0.05 because uncertainty is always resolution divided by 2. And the standard Vernier calipers can measure from 0 millimeter to 150 millimeter. Now move on to micrometer screw gauge. It has a resolution of 0.01 millimeter. That's the smallest division. So the uncertainty is resolution divided by 2, that is 0.005 millimeter. And the range is 0 to 25 millimeter. Now, percentage uncertainty can be calculated in two different ways. One would be using a set of readings, the other one would be resolution of an instrument. But when I say percentage uncertainty, I basically mean the uncertainty, because percentage uncertainty's equation is always the same, uncertainty by measured value. So the two ways you are finding out the percentage uncertainty depends on how you find out the uncertainty. So one way would be using a set of readings, the other one would be using the resolution of an instrument. We'll look at both. First, let's look at using a set of readings. So let's say you have a block and there are three measurements for length, and you take the average of these three lengths. Always remember, the average must be consistent with the number of significant figures of the set of readings. So all of these values are in 3SF, so the mean value must be in 3SF as well. So using a set of readings, uncertainty is given by max minus mean divided by 2. So you look up over here, which one is the max value? This is the max value, this is the mean value. So uncertainty would be max minus mean divided by 2. So max is 20.3, mean is 20.1, and dividing this by 2 gives me 0.1 millimeter. So that is my uncertainty. And bring in the equation for percentage uncertainty, it's always the same. Percentage uncertainty would be uncertainty divided by the average measured value. That is 20.2 times 100%, which will give me 0.5%. So that's one of the ways of finding out the percentage uncertainty, and this was using the set of readings. The second way would be using the resolution of an instrument, and I repeat, when I say using the resolution of an instrument, we'll be finding out the uncertainty. We previously saw from this table that the uncertainty from an instrument is given by its resolution divided by 2. So over here as well, when you see the value given here of the mass of a stack of papers, you can clearly identify what will be the resolution of this balance. So 0.001 would be the resolution, kg of course, would be the resolution of the balance. So if this is the resolution, the uncertainty is resolution divided by 2, that's 0.0005 kg. And the equation for percentage uncertainty is regardless the same, that is uncertainty divided by measured value times 100%. And the standard practice is to give percentage uncertainty to two significant figures. That's why we gave 0.024. Now let's look at some measuring techniques. This is a very common question, that why is it better to measure the thickness of a stack of papers or a stack of coins instead of taking the measurement of a single coin or a single piece of paper. So if you recall that in any measurements, our objective is always to minimize the percentage uncertainty. So let's recall the equation for percentage uncertainty. So percentage uncertainty is uncertainty divided by measured value. So if you're using the same instrument, the uncertainty remains the same. But when you are measuring a stack of papers or a stack of coins, the measured value increases. And guess what? If the measured value increases, the percentage uncertainty decreases. So these are your 2 points for this question. That the measured value increases, the uncertainty remains the same, and the percentage uncertainty decreases. It's also a very common question. The question asks you about the measuring technique you apply with the meter rule. For example, when the meter rule has to be kept vertical, example could be while taking the length readings of a spring. So the meter rule must be clamped in position. This was never considered in previous mark schemes. This is a very new point and it must be included in your examination script. Ensure the meter rule is vertical using a set square. This is the common point. Keep the meter rule close to the mass. Why do you keep it close to the mass? To reduce parallax error. And take readings perpendicularly to the scale. Again, another method to reduce parallax error. You keep the meter rule close to the mass as well as you take readings perpendicularly to the scale. Both of these are done to reduce parallax error. You clamp the meter rule and you use a set square like this to ensure that the meter rule is vertical. Now, two really confusing terms. So I gave an analogy over here. So here you have three letters A in different resolutions. You can clearly see this has a very low resolution, this one low resolution, and this has, compared to this one, the first one, it has a higher resolution. So when it comes to images, what is it that determines the resolution? It's the pixel size. See, here the pixels are very large. That's why you have a low resolution. But over here, you have to zoom it in to see the pixels. So here the pixels are very small pixels, which gives you a high resolution. So how do you relate this, or how do you make it analogous to our instruments? Here you have a meter rule, a vernier caliper, and a micrometer screw gauge. So let's recall the values of the resolutions of these instruments. The resolution of a meter rule is 1 millimeter. The resolution of a vernier caliper is 0.1 millimeter. And the resolution of a micrometer screw gauge is 0.01 millimeter. You can think of these values as the pixel size. The smaller the resolution, the higher, the smaller the value of the resolution, the higher will be the resolution. I know this is where the confusion arises, higher and lower, these two terms. So always remember, smaller value of resolution means a higher resolution. So you can say a micrometer screw gauge has a higher resolution than both a vernier caliper as well as a meter rule. So I repeat, a smaller value of resolution means it has a higher resolution. So while taking measurements, several errors can occur. So two of the most common types of errors would be systematic and random. So let's see what systematic has. When a measurement is consistently erroneous by the same amount every time, it is called a systematic error. The value is larger or smaller by the same amount every time. So how do you deal with systematic errors? Systematic errors can be identified by plotting a suitable graph, and systematic errors can be eliminated by checking for zero error. For example, in a micrometer screw gauge, first you check for zero error and you eliminate the whole error from your measurements. Systematic error can be eliminated, but when it comes to random errors, you cannot eliminate a random error. You can only minimize the effects of random error. But first, let's see what this random error is. This causes measurements to vary unpredictably. So you cannot predict by how much the next measurement will be varied. Unlike systematic errors, where you know for a fact that the value will be higher or lower by the same amount every time. But when it comes to random errors, this varies unpredictably. So how do you deal with random errors? Random errors can be minimized by repeating the measurements and finding the average. This format of the question is very likely to appear in your examinations. So I have compiled calculations and conclusions into one section. So these are the given information. An equation was given and some data were given. So whenever you see an equation appearing in the middle of a question, do not be alarmed if you had never seen this equation before, because had you seen this equation before, they wouldn't have given this inside the question. So this is a custom equation for this specific question. So this was the equation, and these were some values. All you have to do is just plug in the values. W1 goes over here, W1 goes over here, and F goes over here, and density of water goes over here, and you can find out the density of the modeling clay. And you can see, since these two values were two significant figures, the final value was rounded off to two significant figures as well. So this is the standard that most of the times Pearson follows. Now let's move on to the conclusion. Extremely important, and I'm pretty sure this is coming in your actual exam as well. So this is the conclusion part. The previous part was the calculation. This is the conclusion for the same part of the question. Now, the student estimated the percentage uncertainty in his calculated value of density of modeling clay to be 4%. So this is the percentage uncertainty. The density of polymer clay is 1760. Deduce whether the modeling clay could be made from polymer clay. So the value that I calculated over here, is this consistent with polymer clay? This is what the question is asking me to find out. For this type of questions, whether it's acceptable, whether it's suitable, whether it's valid, whether it can be made from this material, for all of these forms of questions, you always find out the percentage difference. How do I find out the percentage difference? So 1760 minus my calculated value divided by 1760. Always use the reference value, the value that the question has given you. So this is the reference value, the accepted value for polymer, right? So I want to see how far off my value is from polymer. So that's why I'm dividing it with the value of polymer times 100%. So my percentage difference is 2.8%. And once you have the percentage difference, you need to compare it with percentage uncertainty. If the percentage difference is less than percentage uncertainty, then and only then it is acceptable. It could be made from polymer, since and only since percentage difference is less than percentage uncertainty. What if the percentage uncertainty is not given? This is actually a common question as well. In a lot of questions in recent years, the percentage uncertainty is not given. So you just find out the percentage uncertainty, and if it is small, you explicitly say that since the percentage difference is small, it is acceptable. Then you have criticism of data. So I have a set of readings and I have to criticize them. So these are given in the question, by the way. So when you look at the values of D, they are consistent with the same number of significant figures, but not the same number of decimal place. So you cannot say inconsistent number of significant figures for this. You have to write inconsistent number of decimal places in the values of D. And K has been calculated. For the calculated quantities, we generally, not a fixed rule, but we generally refer to significant figures. So inconsistent number of significant figures for the values of K. And D has been measured only once. There is no evidence of repeat. So this value, and this value should have been repeated several times and calculated, and we should have calculated a mean, which they did not do. And only 3 sets of readings. The minimum number of readings you should take is 5. but here they have taken only 3. So this could be considered to be one of the points for criticism. Then you have comparing digital and analog instruments. So this is an analog voltmeter and this is the digital voltmeter. So what are the advantages that a digital one has over analog ones? So in digital ones, the percentage uncertainty will be reduced. The multimeter screen display will not cause parallax error because you can clearly see the value from the display. The multimeter can measure to a higher resolution. I already discussed what higher resolution is. Smaller value of resolution gives you a higher resolution. So this is again a confusing bit, smaller and higher. I hope you have it cleared by now. And the digital multimeter will not require interpolation. Interpolation means when you look at the pointer, it can be between two values where there is no division or there is no scale. You have to do some guesswork. But when it comes to digital ones, you get the exact value on the display. There is no need for guesswork. In other words, there is no need for interpolation. Graphs, the most important bit for Unit 3. A lot of people don't know some very important points regarding graphs. Let's look at them. The graph does not have to start from the origin. The scaling has to be done in increment values of 1 to 5 and their multiples of 10, meaning the value can be 1, 2, 3, 4. This is increment of 1, or 0.1, 0.2, 0.3, 0.4, or 10, 20, 30, 40. So this was for increment of 1. I can do the same thing with 2 or 5. What you cannot do is make increments by, let's say, 3 or 4. Those would be considered awkward scales and you will not get the marks for scaling and plotting. Always use crosses for your plotting points. Do not use dots. The best fit line should be thin and continuous with equal number of points above and below the line of best fit. So there are some scatter points. You can see this point, and this point somewhat lie on the graph, but this one is below the line of best fit and this one is above the line of best fit. So this is what you have to try to ensure. Always try and keep equal number of points above and below the line of best fit. Then the gradient that you'll have to find for calculations in the next part of the question must be taken using a large triangle, as large as possible. The gradient must be given to 2SF or 3SF, but never ever in one significant figures. And never use plotting points to calculate the gradient as they may not lie on the graph. Always choose points from the graph. Next, these are some important terms. You can pause the video and go through this. Thanks for watching and good luck with your exam. If you haven't subscribed already, please do.